Hello my friends and welcome back to the You Can Do TV channel. Glass product manufacturing is a multi-stage thermal and mechanical process that combines forming precision with surface finishing and strengthening technologies. Production starts with melting raw glass at high temperature until a homogeneous molten state is achieved. The molten glass is then transferred into molds, where different product shapes are created using a combination of controlled blowing and pressing techniques. During forming, after shaping, glass surfaces undergo polishing to improve optical clarity and surface smoothness. Products requiring enhanced mechanical strength are processed through thermal tempering, where the glass is reheated and rapidly quenched to introduce compressive surface stresses. For decorative or functional applications, additional processes such as lamination, bonding, or decorative attachment are applied, including colored films, printed patterns, or bonded glass components. After final annealing and quality inspection, finished glass products are carefully packaged using protective materials to prevent damage during handling and transportation, ensuring they reach customers in optimal condition. Inside a modern glassworks, skilled hands and controlled heat bring raw materials to life. Lead-free crystal, soda-lime glass, and borosilicate glass are carefully selected, then shaped through mouth-blown and hand-blown techniques that demand precision and experience. Advanced processes such as centrifugal casting, hand pressing, electroplating, and decal printing refine each form, while color spraying and hand painting add distinctive visual character. Custom logo design completes the process, delivering glassware tailored for hotels, bars, and global wholesale markets. Tradition and technology work together to produce durable, refined, and visually striking glassware. The Servo double-gob press machine is a high-precision solution for automated tumbler production designed to deliver consistent quality at high output rates. Molten glass is fed as two precisely controlled gobs into the forming section, where servo-driven mechanisms regulate pressing force, timing, and mold movement with exceptional accuracy. This ensures uniform wall thickness, stable dimensions, and smooth surface finish across each tumbler. The servo control system allows flexible adjustment of pressing parameters, reducing defects and material waste while improving energy efficiency. With synchronized motion control and repeatable cycles, the double-gob press machine is ideal for large-scale production of high-quality glass tumblers. The creation of a Cangini and Tucci lamp is a journey where craftsmanship meets technology. It begins with carefully selected glass tubes, shaped with precision to ensure perfect form and function. Skilled artisans then hand-decorate each piece, giving every lamp its unique character and artistic detail. Meanwhile, advanced LED components are meticulously assembled, integrating modern technology seamlessly into the design. Each element, from the glass to the light source, is calibrated to deliver optimal illumination, efficiency, and visual harmony. Finally, the glass and LED components are carefully combined into the finished lamp, ensuring both durability and flawless performance. The result is a product that reflects timeless design, where tradition, skill, and innovation coexist. Cangini and Tucci lamps illuminate spaces with elegance and ingenuity, showcasing the perfect balance between artisanal artistry and cutting-edge technology. The manufacture of a 10-liter vacuum-jacketed glass reaction vessel is a highly specialized scientific glassblowing process that demands precision, thermal control, and deep material expertise. Production begins with certified borosilicate glass tubing, which is carefully inspected for dimensional accuracy and internal defects. Using high-temperature burners, the glassblower gradually heats and rotates the tubing to achieve uniform viscosity before forming the main vessel body, with a controlled height-to-diameter ratio that replicates plant-scale reactor geometry. The inner reaction chamber is shaped first, followed by the fabrication of the outer jacket. Precise concentric alignment is critical, as the annular space between the two walls will later be evacuated to form the thermal insulation layer. Glass joints, ports, and a DN200 flange are flame-formed and fused, ensuring chemical resistance and mechanical strength. Throughout forming, the vessel is continuously rotated to maintain wall thickness uniformity and geometric stability. Once assembly is complete, the jacket space is sealed and evacuated to create the vacuum jacket, significantly improving thermal efficiency across a wide operating range. The vessel then undergoes controlled annealing to relieve internal stresses. Final stages include dimensional verification, vacuum integrity testing, and visual inspection. The finished 10L vacuum-jacketed vessel is engineered for reliable performance in pilot-scale reactors, supporting precise temperature control, scale-up chemistry, and demanding research applications. Chemical glass instruments are engineered to operate reliably under extreme thermal, chemical, and mechanical conditions. Using high-purity borosilicate glass, each component is formed through controlled heating, rotation, and precision shaping to achieve uniform wall thickness and structural stability. Advanced glassworking techniques are applied to produce reactors, evaporators, and distillation systems with excellent thermal shock resistance and chemical inertness. Throughout production, strict quality control ensures accurate tolerances, smooth internal surfaces, and long service life. These instruments are designed to support complex processes such as evaporation, separation, and purification in pharmaceutical, chemical, and advanced material applications where precision and reliability are critical. In a world increasingly dominated by digital technology, the charm of the primitive, the original, still holds a unique allure. Imagine taking a century-old incandescent bulb and rethinking it, not just as a source of light, but as a work of design, a piece that evokes emotion while preserving its classic essence. At the heart of this transformation is the commitment to creativity and design. Traditional mass production, focused solely on function, is no longer enough. Companies must embed imagination into their products to survive and thrive. By turning ordinary incandescent bulbs into designer objects, each piece becomes a blend of technical precision and artistic expression, offering both aesthetic value and functional performance. The process begins with careful selection of materials and precise shaping of the bulb, respecting its original form while enhancing it through design elements. Each component, from the filament to the glass envelope, is crafted with attention to detail. Beyond manufacturing, the design approach considers how light interacts with space, how the product engages emotionally with users, and how it can become a symbol of craftsmanship and creativity. This philosophy not only preserves the incandescent bulb's heritage, but elevates it, demonstrating that even traditional analog technology can find new relevance in a modern, design-focused context. By embracing creativity as a core principle, companies can create products with lasting value, appealing both to functionality and the timeless human desire for beauty. Through this approach, what was once a simple source of light transforms into a statement piece, a testament to innovation, artistry, and the enduring power of thoughtful design. Cangini and Tucci's production process is a meticulous blend of craftsmanship and technical precision. Skilled artisans start with hand-blown glass tubes, carefully shaping each piece using heat and flame techniques to achieve the desired form. Decorative patterns are applied by hand, often with delicate brushes or stencils, before being reheated to fuse the designs into the glass. Every step, from flame working the glass to hand finishing details, requires expert control of temperature, timing, and material handling, producing lamps that are as technically refined as they are visually stunning. The production of centrifugal swing-cast glass charger plates combines precision and artistry. Molten glass is poured into spinning molds, using centrifugal force to shape even, thin plates. Heat-bending techniques refine curves and edges, ensuring uniformity. Each piece is inspected for quality before cooling, producing elegant, durable glass plates ready for functional and decorative use. The manufacturing of a round-bottom flask begins with heating and blowing a borosilicate glass tube into the required spherical form. Skilled glassworkers carefully shape and finish the bottom to ensure uniform wall thickness and precise geometry. Once formed, the flask is placed in an annealing furnace overnight, where controlled cooling relieves internal stresses and guarantees thermal stability, strength, and long-term reliability for laboratory use. At the intersection of ceramic craftsmanship and lighting technology, this workshop demonstrates a tightly controlled production sequence where material science defines the final form. The process begins with a ceramic shell, formulated from a precise mineral composition. Feldspar at 9% promotes vitrification, while silica sand at 13% ensures structural rigidity. Pottery stone, comprising 26%, provides body strength, complemented by clay at 15% for workability. Kaolin at 7% enhances thermal stability, and terra alba at 30% delivers a refined surface texture. These raw materials are carefully mixed, shaped, and fired to achieve dimensional accuracy and heat resistance suitable for lighting applications. Once the ceramic housing is completed, attention shifts to bulb fabrication. Glass components are formed and processed under controlled thermal conditions, with burner temperatures maintained between 560 and 580 degrees Celsius to ensure uniform glass flow and precise sealing. Vacuum generation is a critical step, with internal pressure reduced to a range of 0.002 to 0.008 millimeters of mercury, minimizing impurities and extending filament performance. The final stage involves precise assembly, where the ceramic body and glass bulb are integrated into a single unit. Each connection is aligned and secured to guarantee electrical stability, thermal durability, and consistent light output. This technical visit provides a clear view of a high-capacity LED lamp production line where precision assembly and thermal control are central to product performance. The process begins with incoming LED materials being separated into individual components. LED modules are prepared and transferred to the attraction and positioning stage, where they are matched with aluminum lamp bodies designed for effective heat dissipation. Each lamp body moves along the conveyor to a thermal preparation station, where automated equipment cleans the contact surface and applies thermal paste. This step is critical to ensure efficient heat transfer between the LED module and the aluminum housing. Operators then accurately place the LED module onto the lamp body, and hydraulic presses secure the components together, guaranteeing stable thermal conductivity. The assembled units are inverted and transferred to the electrical assembly stage. Here, AC wires are installed, aligned, and trimmed to specification. An automated machine presses the E27 base onto the lamp body, reinforcing the mechanical structure. Excess material is removed, and protective caps are applied. Optical lenses are then mounted, followed by the first lighting test to immediately reject defective units. Qualified lamps proceed to aging, where they operate continuously for 30 minutes to verify stability and reliability. After visual and functional inspection, finished lamps enter the automated packaging stage. This production line is capable of delivering up to 20,000 LED lamps per day, reflecting a highly efficient and standardized manufacturing system. Scientific glassblowing at super large scale demands an exceptionally high level of technical skill, experience, and material control. In the project to manufacture a monumental lighting installation for an ultra-luxury hotel in London, each glass component exceeded 500 millimeters in diameter, far beyond the dimensions typically associated with hand-blown glass. Throughout the shaping process, the glass must be continuously rotated in conjunction with a high-temperature blowtorch to ensure even heat distribution and prevent deformation or collapse. Once the material reaches optimal plasticity, it is introduced into a mechanized roller system to achieve precise geometric control. The glass blank is axially stretched and rolled evenly across synchronized rotating rollers, allowing wall thickness to be distributed uniformly along the tube or lamp body. Roller speed, pulling force, and spacing are machine-controlled to minimize diameter deviations and to prevent localized sagging or distortion. This roller-assisted forming process makes it possible to produce components larger than 500 millimeters with a high degree of roundness while maintaining thermal stability. After the desired shape is achieved, the glass is transferred to an annealing furnace, where controlled cooling relieves internal stresses, ensuring long-term mechanical strength. The installation of the Jingzhou Great Wall 100-liter jacketed glass reactor is a structured, precision-focused process designed to ensure mechanical stability, sealing integrity, and reliable thermal performance. The procedure begins with applying a thin, even layer of vacuum silicone grease to all ground glass joints. This step is critical to improving airtightness, preventing seizure, and facilitating future disassembly during maintenance. Next, the stirring paddle is carefully inserted into the reactor vessel, ensuring proper alignment with the central axis. The rotary motor is then mounted onto the reactor frame, followed by securely fixing the stirring paddle to the motor shaft. Accurate coupling at this stage is essential to avoid vibration, uneven mixing, or excessive load on the motor during operation. The motor support pole is subsequently installed to provide additional structural stability and maintain precise vertical alignment. A silicone rubber shroud ring is fitted around the vessel flange to enhance sealing performance and protect the glass interface from mechanical stress. The condenser is then installed onto the designated port, ensuring efficient vapor condensation and reflux control during reactions. Following this, the tray for the collecting bottle is mounted, allowing safe and stable placement of condensate receivers. The solid charging port plug is installed next, providing a sealed access point for adding solid reactants under controlled conditions. Finally, the stainless steel thermal insulation hose is connected to the reactor jacket. This hose enables the circulation of heating or cooling fluids while minimizing heat loss and protecting operators from high surface temperatures. Once assembly is complete, all connections are inspected to confirm alignment, sealing, and mechanical security, ensuring the 100-liter jacketed glass reactor is ready for safe and efficient operation in laboratory or pilot-scale process environments. The production of glass bottles and jars involves precise flame polishing to achieve smooth, flawless surfaces. After forming, each piece is carefully exposed to controlled flames, which melt and refine the edges, eliminating roughness and imperfections. This process enhances both the aesthetic quality and functional integrity of the glass, ensuring durability and safety for storage. Flame polishing is a critical finishing step in glass manufacturing, delivering clear, polished bottles and jars ready for packaging and consumer use. At the final stage of spirits bottle production, after the glass is heated to the proper molten temperature, it is carefully poured or fed into molds corresponding to the desired bottle size, 500 milliliters, 700 milliliters, or 750 milliliters. The molds shape the hot glass into its final form, ensuring uniform walls, neck, and base. Once molded, the bottles are cooled gradually in an annealing layer to relieve internal stresses, preventing cracks or deformation. This controlled process guarantees that each bottle achieves the required strength, dimensional accuracy, and clarity, ready for further inspection, cleaning, and packaging before filling with spirits. From raw glass to a precisely formed reactor vessel, each stage combines skilled craftsmanship with scientific control. High borosilicate glass is heated, fused, and refined at extreme temperatures, ensuring exceptional durability, optical clarity, and chemical resistance to meet the rigorous demands of modern laboratories and production environments. This presents an overview of integrated laboratory equipment used for temperature control, vacuum control, and chemical reaction processes. The systems include jacketed glass reactors, rotary evaporators, circulating chillers, dynamic temperature controllers, and vacuum pumps, all designed to operate as a coordinated unit. Each device is engineered to maintain precise thermal stability, controlled pressure, and efficient mass transfer during distillation, evaporation, or synthesis. Such equipment is widely applied in chemical, pharmaceutical, and biological laboratories, as well as in materials and energy research. Modular design, standardized connections, and certified safety features ensure reliable operation, flexible configuration, and consistent performance in demanding scientific and industrial. Glass sorting plays a key role in sustainable production. A new glass product or container can contain up to 100% recycled glass without any loss of quality. Glass is unique among waste materials because it can be recycled endlessly. Proper separation by color and cleanliness ensures efficient melting, energy savings, and consistent material properties in new glass manufacturing. A 3-layer glass reactor thermal shield enhances process stability by minimizing heat loss and improving temperature control. The insulated structure supports vacuum operation while maintaining full visual access. Its corrosion-resistant design ensures safety, energy efficiency, and consistent performance in advanced chemical and pharmaceutical laboratory applications. Integrated with an automated heating furnace, the KUKA industrial robot coordinates material handling and process timing with high precision. The furnace provides controlled thermal conditions for glass forming or component treatment, while the robot synchronizes loading, unloading, and positioning operations. The JCL press machine is designed for the high-precision production of glass refrigerator containers and other glass tableware. Molten glass is accurately fed into the mold, where controlled pressing ensures uniform wall thickness and consistent geometry. Automated temperature regulation and synchronized pressing cycles improve forming accuracy, reduce defects, and support stable, repeatable output suitable for large-scale industrial glass production. Every piece of glass begins its life in intense heat, where precision and material control define the final performance. Rotary evaporator collection flasks are manufactured from Borosilicate glass 3.3, selected for its low thermal expansion, high chemical resistance, and long-term stability under laboratory conditions. Skilled glassblowers form each flask at high temperatures, carefully controlling wall thickness, geometry, and joint alignment. Once shaped, the glass undergoes a controlled annealing process, allowing internal stresses to be released gradually. This step is critical to achieving optical clarity, mechanical strength, and reliable sealing during vacuum operation and thermal cycling. From the initial molten state to the final transparent form, every stage is governed by strict process control and craftsmanship. The result is laboratory glassware that delivers consistent performance, precise measurements, and dependable service life. True reliability in scientific application starts at the source, with glass engineered to meet the highest standards of accuracy and durability. At Sengzhou Chanyo Glassware, molten glass is shaped using continuous rotary machines as part of the glassblowing process. The high-temperature glass flows onto rotating rollers, allowing precise stretching and forming of items like spheres or decorative pieces. Skilled control of heat, rotation speed, and pressure ensures uniform thickness, clarity, and durability, producing high-quality, unique glassware. A professional eyeglass manufacturer follows a comprehensive production process to ensure high-quality frames and finished products. The process begins with the overall design of the eyeglasses, including shape, size, and style specifications. Raw material sheets for the frames are then cut into uniform pieces, ready for precision machining. These pieces are loaded into CNC machines, which accurately cut and shape each component according to the design specifications. Following the cutting, the frame components are assembled, ensuring proper alignment and fit of all parts. To achieve a smooth, polished finish, the frames undergo polishing using tumbling with abrasive media, such as small beads or pebbles, which removes rough edges and imparts a uniform shine. Each finished frame is carefully inspected for quality, including checks for surface finish, dimensional accuracy, and structural integrity. Only frames that pass these inspections proceed to the packaging stage, where they are carefully boxed and prepared for shipment. This systematic approach, combining advanced CNC technology, skilled assembly, and precision polishing, ensures that every pair of eyeglasses meets professional standards for durability, aesthetics, and comfort, providing customers with a reliable and high-quality product. From tiny dropping funnels used in delicate chemical reactions to massive 500-liter reactors in pilot plants, every component is the result of meticulous craftsmanship and advanced processing techniques. Their expertise spans from small R&D apparatus, such as beakers, flasks, and dropping funnels, to large-scale process equipment with capacities up to 500 liters. Large glassware engineers fabricate items up to 620 mm outer diameter, employing custom lathes, jigs, and advanced processing methods to achieve complex shapes and precise tolerances. The lab group handles small volume products under 5 liters, using manual techniques for standard, custom, and repair glassware. Special processes, such as distillation heads and Oldershaw joints, are performed with exacting control, ensuring mechanical strength and ease of use. The machining group focuses on mass production of joints and edges, using automated machines to stabilize quality and reduce processing time. The grind and polishing group performs precision finishing of glass-to-glass joints, including edge grinding, drilling, and taper adjustment, maintaining high dimensional accuracy while prioritizing operator safety. AG also produces borosilicate and quartz glass components for physico-chemical applications, large-scale process plants, and optical fiber equipment, demonstrating high heat resistance, chemical purity, and structural integrity. The company's 2014 plant expansion centralized all processes under one roof, improving workflow efficiency, quality control, and production capacity. Continuous investment in automation and precision tooling allows AG to deliver both custom one-off products and high-volume components with consistent performance. Through rigorous process control, skilled craftsmanship, and innovative engineering, AG ensures that each product meets strict technical specifications, providing reliable solutions for laboratory research, chemical processing, and industrial applications. The company continues to develop talent and advanced processing technologies, maintaining over 65 years of expertise in high-precision glass manufacturing. Precision and quality are at the heart of laboratory glassware production, starting with Buro 3.3 glass, which is cut into tubes of precise dimensions. These tubes are then blown into beaker shapes, followed by inspection (IQC) to ensure quality. Next, beakers are printed with measurement markings, fired in a furnace for durability, and finally packaged for laboratory use. From raw glass to a precise laboratory instrument, the making of a 100 milliliters measuring cylinder is a meticulous process. Molten glass is shaped into a narrow cylinder, ensuring uniform thickness and stability. After cooling, the cylinder is carefully calibrated with accurate graduated markings. A spout is added for controlled pouring, and each unit undergoes strict quality checks. The result is a durable, high-precision measuring cylinder, designed to deliver reliable liquid measurements for scientific experiments and laboratory use, minimizing errors and preventing spills. Every modern window screen and architectural glass panel starts as raw materials transformed through a meticulous process. The float glass manufacturing process begins by precisely mixing raw materials: 60% sand, 20% soda, along with limestone, dolomite, feldspar, sulfate, and recycled glass cullet. This mixture forms the glass batch, which is fed into a melting furnace, heated to around 800 degrees Fahrenheit, 540 degrees Celsius. Inside the furnace, the raw materials melt completely, transforming into a uniform molten glass. The molten glass is then carefully poured onto a bath of molten tin, maintained at 100 degrees Celsius. This allows the glass to spread evenly and form a smooth, flat ribbon. Top rollers guide the glass, ensuring uniform thickness and surface quality. Throughout the process, operators perform routine visual inspections and maintenance to maintain furnace longevity and glass consistency. After floating, the glass passes through a controlled cooling section, gradually dropping to around 70 degrees Celsius. Advanced control systems monitor the furnace, tin bath, and layer to ensure consistent quality. The process centers on controlled heating and precise rotation to achieve consistent form and accuracy. Borosilicate glass tubes are introduced into high-temperature burners, where the glass is gradually heated until it reaches a uniform, plastic state. During heating, the workpiece is continuously rotated to ensure even heat distribution and symmetrical wall thickness. Once softened, the glass is shaped while still rotating, allowing gravity and centrifugal force to help define the flask body and neck with high-dimensional consistency. The formed flask is then transferred to an annealing furnace, where slow, controlled cooling stabilizes the structure and eliminates internal stress, ensuring durability and long-term dimensional stability. At extreme temperatures where precision leaves no room for error, raw quartz begins its transformation into high-performance glass. Under intense heat, high-purity quartz is fed into specialized furnaces, where temperature, draw speed, and pressure are continuously monitored to maintain absolute control over clarity and geometry. Using a direct draw process, molten quartz is formed into tubes and rods with exact diameters and wall thicknesses. As the material cools, each piece is cut, resized, and finished to achieve smooth edges and consistent dimensions. Additional thermal treatment further refines purity and structural stability. Every quartz component is then subjected to strict visual and dimensional inspection. Only pieces that meet demanding technical tolerances proceed to the next stage, ensuring reliability, high performance, and suitability for advanced industrial and scientific applications. Behind every automotive windshield is a tightly controlled manufacturing process where safety, precision, and consistency are paramount. This is clearly demonstrated in modern automotive glass production in Ukraine, where advanced technologies and a closed-loop production cycle ensure stable quality at every stage. Design and engineering begin with detailed digital modeling, allowing even minor geometric and optical requirements to be accurately defined. High-precision cutting, shaping, and tempering systems from global equipment manufacturers are used to produce complex glass forms with consistent thickness and strength. Raw materials are sourced exclusively from reliable European suppliers to guarantee optical clarity and mechanical performance. Throughout production, glass components undergo rigorous laboratory testing to meet international safety standards. Tempered glass is widely applied for roofs and sliding windows, while windshield manufacturing is fully automated to minimize human influence and variation. In addition to structural integrity, the finished glass provides UV protection, noise reduction, and thermal insulation. The result is automotive glass engineered to perform reliably under demanding real-world conditions. At a modern toughened glass manufacturing facility, the production process is engineered around precision, automation, and energy efficiency. Raw float glass sheets are first transferred from the stock area using an overhead crane system, ensuring safe handling of large and thin panels. At the cutting line, CNC-controlled cutting tables automatically size the glass according to production specifications, minimizing dimensional tolerance and material loss. After cutting, the glass moves to the edge processing section, where edging and seaming machines grind and polish the edges to remove micro cracks that could cause failure during heat treatment. The sheets are then thoroughly cleaned and dried in an automated washing line to eliminate dust and residues before thermal processing. The core operation takes place in the tempering furnace. Here, glass sheets are heated uniformly to approximately 700 degrees Celsius and then rapidly cooled in the quenching section using high-pressure air jets. This controlled thermal shock induces compressive stress on the surface and tensile stress in the core, significantly increasing mechanical strength and thermal resistance. For insulated glass unit (IGU) production, tempered sheets are assembled with aluminum spacers sealed and filled with inert argon gas to enhance thermal and acoustic insulation. The units are pressed to ensure airtight bonding. In the lamination line, PVB inner layers are placed between two tempered glass sheets, pressed, and then processed in an autoclave under high heat and pressure to form a permanent laminated structure. Throughout production, quality control is conducted in a dedicated laboratory, where optical quality, strength, and dimensional accuracy are verified. The finished toughened, laminated, and IGU glass products are prepared for transport, ensuring compliance with structural and safety standards for architectural and industrial applications. In this sequence, a flip-flow recycling screen operates with advanced TPP double-throw technology. The screening deck reaches accelerations of up to 70 grams, allowing efficient separation of fine and sticky materials. The intense oscillating motion promotes continuous self-cleaning of the screen media, maintaining consistent throughput and reliable performance in recycling processes. Set among tall buildings in downtown Hiroshima, the Optical Glass House transforms a dense urban site into a calm, light-focused living environment. The street-facing facade is constructed from approximately 6,000 solid optical glass blocks produced through precision casting and slow cooling to ensure internal clarity and structural stability. Each block acts as a light diffuser, refracting daylight deep into the interior while maintaining acoustic insulation and visual privacy. The glass mass functions as a thermal buffer, reducing heat transfer and external noise. Through careful material control and assembly accuracy, the facade operates not as a window, but as a luminous, load-bearing architectural element. A modern glazing installation workflow where precision handling and equipment reliability are critical from the very first lift. A Manitou telehandler works in combination with the TGT Hermes 900 vacuum grab unit to deliver precise, stable handling for facade glazing operations. The vacuum lifter securely grips each glass pane through multiple suction pads, evenly distributing loads and reducing localized stress. Smooth hydraulic control allows accurate lifting, rotation, and positioning even when working at height or in restricted spaces. Throughout the process, vacuum pressure is continuously monitored to ensure a secure hold during movement and placement. The telehandler's reach, stability, and lifting capacity make it ideal for handling large-format glazing safely and efficiently. This mechanized installation method minimizes manual handling, improves alignment accuracy, and significantly enhances on-site safety, making it well-suited for modern architectural projects involving oversized glass panels. This sequence demonstrates the correct handling and installation of Glassapore foam glass. The material is spread and leveled to form a stable base with high internal friction, making it walkable immediately after placement. On smaller surfaces, compaction is performed using a 90 to 100 kilogram vibratory plate, typically with 2 passes. Glassapore is compacted layer by layer, reaching 15 to 20% compression. A fiber fabric is applied to separate, overlying construction layers and ensure long-term stability. From recycled glass to a high-performance construction material, foam glass gravel undergoes a precisely controlled production process. Finely ground recycled glass is blended with organic activators and heated to approximately 900 degrees Celsius, where controlled foaming creates millions of closed micropores. This cellular structure delivers low weight, high compressive strength, and permanent thermal insulation. On-site, foam glass gravel is installed as a load-bearing thermal insulation layer beneath foundation slabs. A geotextile is first placed as a separation layer, followed by uniform distribution of the material. Compaction of approximately 30% interlocks the grains, creating a stable, drainage-capable base. Installation can be performed in single or multiple layers depending on thickness requirements, combining insulation and drainage in one efficient construction step. Step inside the precision-driven world of Migo Glass, where advanced engineering transforms raw glass into high-performance laminated safety solutions. Laminated glass processing follows a strictly controlled, multi-stage manufacturing sequence to ensure exceptional strength, clarity, and long-term durability. The workflow starts with precision glass cutting, where raw sheets are shaped to exact technical specifications. Each panel then passes through edge grinding to remove sharp edges and enhance mechanical stability. Thorough cleaning and drying eliminate all surface contaminants before heat treatment. The glass is subsequently tempered to significantly increase impact resistance and thermal strength. In the laminating stage, tempered panels are combined with high-performance SGP interlayers. Controlled preheating activates the bonding process, while vacuum treatment removes trapped air and ensures uniform adhesion across the entire surface. The process concludes with rigorous quality inspection, verifying optical clarity, dimensional accuracy, and structural integrity. This comprehensive production method delivers laminated glass engineered for demanding architectural, structural, and safety-critical applications. The production of Saint-Gobain float glass begins with carefully measured raw materials, including sand, soda ash, limestone, dolomite, salt cake, and recycled glass. These ingredients are melted in a furnace at approximately 1,500 degrees Celsius to form molten glass. The molten glass is then floated onto a bath of molten tin, creating a perfectly flat surface and uniform thickness. Next, the glass enters a layer, where it is slowly cooled to relieve internal stresses. A laser detection system inspects every square centimeter for imperfections before cutting. For advanced applications, the glass can be coated using a magnetron process, depositing microscopic metal oxide layers under vacuum to enhance thermal insulation, solar control, and energy efficiency. Laminated glass is produced by sandwiching a PVB layer between two cleaned glass sheets. Rollers remove air bubbles, and the assembly is heated in an oven at up to 250 degrees Celsius in a pressurized environment to bond the layers. The final laminated glass is impact resistant, retaining shards upon breakage and protecting interiors from UV damage. Sustainability is central. Around 30% of each sheet comes from recycled glass, reducing carbon dioxide emissions by over 375,000 tons annually. Every stage, from raw materials to coating and lamination, is carefully controlled to deliver high-performance, durable, and environmentally responsible glass products. Every day, hundreds of tons of raw materials enter the batch house, where they are precisely measured, tested, and blended into a dry batch. Broken glass, or cullet, is recycled back into the mix, reducing raw material usage and supporting sustainability. The full batch is then charged into a furnace, reaching up to 3,000 degree F, transforming the materials into a molten, 4-foot deep pool of liquid glass. From the furnace, the molten glass flows onto a molten tin bath, spreading into a flat ribbon. Skilled technicians monitor and adjust the glass thickness, ensuring uniformity. The ribbon then passes through the annealing layer, where it cools gradually to relieve internal stresses. In the mass air section, air jets bring the glass temperature down to safe handling levels. Advanced inspection systems, including cameras and lasers, detect defects. The glass is then cut with XY cutters and snapped along scored lines. Edges are trimmed, and trimmings are recycled. Finally, each pane moves through an automated routing system to the packing station, where it is carefully wrapped, labeled, and prepared for transport. Every step ensures precision, clarity, and high-quality window glass. Security glass, even when designed for high protection, has defined limits under extreme conditions. Standard 19mm TGH and 19mm TGH safety-filmed glass, as well as 11.5mm and 13.5mm anti-bandit panels, can be penetrated when subjected to sustained or high-energy attacks. Even BR4 ballistic glass at 32mm, engineered for bullet resistance, may fail under projectiles exceeding its rated caliber or velocity. Testing reveals that each type absorbs and disperses energy differently. Laminated films and multiple layers delay penetration, but ultimately structural limits are reached. These results underscore the importance of selecting the correct glass type for specific threat levels and supplementing it with additional protective measures such as barriers or alarms. ESG Secure P8B glass, at 13 mm, is engineered for superior performance and undergoes multi-standard testing. Manual attack resistance is certified to EN 356, intruder resistance to LPS 1270, ballistic protection to EN 1063, and blast resistance to ISO 16933. During testing, energy absorption, delamination, and structural integrity are carefully measured. Layers and films are designed to dissipate impact forces while maintaining transparency. These controlled tests validate the toughness of ESG secure glass, proving it is not only resistant, but dependable in demanding security applications.